Welcome to SpaceTime's cosmic journey of discovery. In this episode, we'll dive deep into the heart of the universe's greatest mysteries, black holes, and specifically their ultimate fate. If you've ever thought black holes were immortal, eternal prisons of space and time, prepare to have your mind changed. Don't forget to subscribe to the channel so you don't miss out on other exciting space exploration videos. If you find the video interesting and useful, please like and share to support us. First, let's briefly recap what black holes are. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They form from the collapse of massive stars at the end of their life cycle, or from the accumulation of matter at the centers of galaxies. The boundary beyond which there's no return is called the event horizon. Inside the event horizon, all paths lead to a singularity, a point where density and gravity become infinite, where the laws of physics as we know them seemingly break down. For decades, physicists believed black holes were entirely black objects, capable only of growing by swallowing surrounding matter and energy. They were seen as eternal gravitational machines that never died. This belief stemmed from Einstein's theory of general relativity, which describes gravity as the curvature of spacetime. According to this theory, once matter falls into a black hole, it disappears forever, never to escape. Before Stephen Hawking published his revolutionary theory, scientists envisioned black holes as eternal prisons. Once anything crossed the event horizon, the point of no return, it would be forever confined, with no escape, not even light. According to Einstein's theory of general relativity, black holes were predicted to be entirely black entities, emitting no form of radiation. They were seen as immortal swallowing machines, growing in size over time as they continuously absorbed surrounding matter. The idea of a black hole dying, evaporating, and disappearing was alien, even absurd, to many physicists at the time. This was because if black holes were absolutely black, as their name suggested, they couldn't lose energy, and therefore couldn't lose mass. A black hole, once formed, would exist forever, perhaps until the very end of the universe, or grow incessantly until it consumed everything. This notion shaped our understanding of black holes for decades, transforming them into the ultimate symbols of eternity and impenetrable mystery in space and time. It was a prospect both terrifying and fascinating, a cosmic force we could only observe from afar without being able to influence or change. This view created a major asymmetry in the universe. Everything else had a beginning and an end, but black holes seemed to be the sole exception. In 1974, the brilliant physicist Stephen Hawking put forth an idea that shook the foundations of physics. He proposed that black holes are not black at all, as we once thought, but actually emit a faint form of radiation from their event horizon.
This radiation was later named Hawking radiation, and its implications were profound. Black holes have a temperature, and therefore they can lose energy, lose mass, and eventually evaporate, vanishing from existence. This was a bold idea because it combined the two main pillars of modern physics: Einstein's general relativity, which describes space, time, and gravity, and quantum mechanics, which describes the world of subatomic particles. Before Hawking, no one thought these two theories could intersect in this way, in the context of black holes. This discovery not only changed how we perceive black holes, but also opened a new door to a deeper understanding of the relationship between gravity and quantum mechanics, two fields that scientists are still striving to unify into a theory of everything. Hawking demonstrated that the universe, even in seemingly silent places like a black hole's event horizon, is ceaselessly vibrant at the quantum level. To understand Hawking radiation, we need to dive deep into the strange world of quantum mechanics, where space is never truly empty. Even in a perfect vacuum, virtual particles constantly appear and disappear in matter-antimatter pairs. This phenomenon is known as quantum foam or quantum fluctuations. These virtual particle pairs, such as an electron and a positron, emerge from the vacuum's stored energy, exist for an extremely short time, and then annihilate each other.
However, what happens if such a pair of virtual particles forms right at a black hole's event horizon? Here, the gravitational force is extremely powerful, creating an immense space-time distortion. Hawking realized that in this special situation, one of the two particles could fall into the black hole, while the other, carrying positive energy, fortunately escapes into space. This escaping particle is the Hawking radiation we're discussing. In essence, the energy of this escaping particle does not come from something inside the black hole. Instead, it is taken from the black hole's own mass. According to the principle of energy conservation, if a particle with positive energy escapes, the black hole must lose an equivalent amount of energy. And according to the famous formula E equals mc squared, losing energy means losing mass. This process occurs continuously, with billions upon billions of virtual particle pairs appearing and disappearing every second, causing the black hole to gradually glow and lose mass. The emission of Hawking radiation not only means that black holes are losing mass, but also implies that they have a certain temperature. Typically, a hot object emits radiation. Therefore, the fact that black holes emit Hawking radiation suggests that they are not absolutely cold as once thought, but possess a very tiny temperature, inversely proportional to their mass. This means smaller black holes are hotter and radiate more strongly than larger ones. A black hole with the mass of the Sun would have an extremely low temperature, only about 1/1,000,000th of a Kelvin, far lower than the cosmic microwave background radiation. Consequently, in the current cosmic environment, stellar mass and supermassive black holes do not actually evaporate. On the contrary, they are absorbing more cosmic background radiation than they emit via Hawking radiation, causing them to continue growing. However, this will change as the universe becomes colder and sparser in the distant future. When Hawking radiation surpasses the rate of energy absorption, black holes will begin the process of true evaporation. This process is very slow at first, but will accelerate significantly as the black hole loses mass and becomes smaller, thus hotter and radiating more intensely. Ultimately, an evaporating black hole will shrink to an incredibly tiny size, and in the final moments of its existence, it will emit an extremely powerful burst of radiation, a small gamma-ray burst, before disappearing completely. The time it takes for a black hole to completely evaporate depends heavily on its initial mass. Small black holes, known as primordial black holes, hypothesized to have formed in the early universe with very small masses, sometimes just that of a mountain. A black hole with the mass of 1 ton would evaporate in about 1/1000,000th of a second, producing an explosion equivalent to millions of nuclear bombs. A mountain mass black hole would take about several 100 million years to fully evaporate, a long time, but still very small compared to the age of the universe. In contrast, stellar mass black holes, with masses a few times that of the Sun, would take an enormous amount of time to evaporate.
It is estimated that a solar mass black hole would take about 10 to the 67th years to completely evaporate. To put this into perspective, this number is many billions of billions of billions of billions of times the current age of the universe.
Even more astonishing are supermassive black holes, like Sagittarius A, at the center of our galaxy, with masses millions to billions of times that of the Sun. A supermassive black hole with a mass of 10 million suns would take about 10 to the 87th years to evaporate. These are numbers beyond human comprehension, indicating that for large black holes, they are indeed nearly eternal entities within the context of the universe's lifespan as we know it. However, theoretically, even they will have a final doomsday, when they dissipate into a last wave of radiation, leaving behind an empty space. One of the most controversial consequences of Hawking radiation is the black hole information paradox. According to quantum mechanics, information can never be destroyed. Information here is not what we commonly think of, but rather the detailed quantum state of every particle. If you throw a book into a black hole, the book will be crushed, but in principle, the quantum information about every atom and molecule composing it must still be preserved in some form. However, when a black hole completely evaporates through Hawking radiation, it only emits pure thermal radiation, carrying no information about what fell into it. This means that all information about the object swallowed by the black hole seemingly vanishes forever, violating the principle of information conservation in quantum mechanics. This is an extremely serious problem because it shakes one of the foundations of quantum physics. Scientists have proposed many potential solutions to resolve this paradox, each with profound implications. Some suggest that information is not truly lost, but encoded in some way on the event horizon, perhaps in the form of firewalls or complex quantum structures called fuzzballs. Other theories propose that information might escape with Hawking radiation, but in a very subtle, complex form that we cannot yet decipher. Another possibility is that information is not destroyed, but persists in the black hole's final remnant after evaporation, although this concept remains vague. Solving the black hole information paradox is one of the biggest challenges in modern physics, and it may require a new, more comprehensive theory to unify quantum mechanics and general relativity. Although Hawking radiation is one of the most important predictions of modern theoretical physics, its direct observation remains an enormous challenge. Hawking radiation from stellar mass and supermassive black holes is too faint for us to detect with current technology. Their temperature is much lower than the cosmic microwave background radiation, causing them to be lost in the cosmic noise. To observe it directly, we would need to search for super-small primordial black holes, if they truly exist, as they would emit significantly stronger radiation as they evaporate. To date, there is no direct experimental evidence confirming the existence of Hawking radiation. However, physicists have conducted analogous experiments in laboratories, creating acoustic black holes or optical black holes using special environments like Bose-Einstein condensates. In these systems, sound waves or light play a similar role to light in a black hole's gravitational field, and scientists have observed phenomena analogous to Hawking radiation. While these are not true black holes, these experiments provide crucial indirect evidence supporting Hawking's theoretical predictions. The future of studying Hawking radiation may lie in extremely sensitive next-generation telescopes or new-generation gravitational wave detectors capable of detecting small energy bursts from evaporating primordial black holes. Directly confirming Hawking radiation would be a monumental breakthrough, opening a new era in astrophysics and quantum physics. So, what does the idea that black holes can evaporate and disappear mean for the existence of the universe? It completely changes our notion of eternity. If even the most powerful entities in the universe have an expiration date, then so does everything else. In an extremely distant future, When the last stars have burned out, when galaxies have dispersed, and the universe becomes cold and empty, what remains might just be black holes. But even they will slowly dissipate, a final radiation of energy and information. If this theory is correct, the universe will eventually become a feast of photons and leptons when all matter has been completely broken down and all traces of complex structures have vanished. This is a lonely, cold prospect, but it also reveals a complete cycle of existence, from formation to disappearance, even for seemingly indestructible structures. Hawking radiation is not just a physical prediction, it is a profound insight into the nature of reality. A reminder that nothing is eternal in this universe, except, perhaps, the very laws of physics that govern it all. Our journey of exploring black holes is far from over. From their birth, evolution, to their eventual death, each stage holds profound mysteries. In the next video, we'll continue to explore an equally dynamic cosmic cycle, the life of stars. We'll learn how stars form from clouds of dust and gas, burn brightly for billions of years, and eventually end their lives spectacularly, sometimes creating the very black holes we've just discussed. Subscribe to the channel so you don't miss this exciting next part.